Hi everyone! In this video we are going to go over the reduction of alkynes. So we've seen this previously with alkenes. So recall that if you want to turn an alkene into an alkane, so going from a double bond to a single bond, you need to add hydrogen across that bond. And remember that this reaction is called catalytic hydrogenation. So that means we, of course, need a catalyst, and we saw that there were multiple catalysts we could use. We could use platinum, palladium mixed with carbon, nickel, or Wilkinson's catalyst. I'll just arbitrarily choose palladium mixed with carbon. But you could put the other catalyst there as well. So how do we do the same reaction with an alkyne? How do we go from a triple bond to a single bond? So we're going to use the same exact reagents. So let's say we start with this triple bond in a 4-carbon chain. So this is butane. And let's say we add one equivalent of hydrogen with palladium mixed with carbon. We would actually produce an intermediate, which is the cis alkene. And remember that hydrogen adds via syn addition. So the hydrogen atoms are adding onto the same side of the triple bond. So that means we're going to end up with a cis alkene. Now, in reality, we actually don't see this intermediate because there's no good way to add just one equivalent of hydrogen. We would actually have an excess of hydrogen present. So we can't stop at the alkene in this case. So this intermediate is actually not observed. And then I'll write syn addition up above just so we remember why we get the cis form. So in reality, we don't see that intermediate. We actually go straight to the product, which is the alkane. So again, hydrogen is in excess. Therefore, we do not observe the alkene. But what if we wanted to turn a triple bond into a double bond? So what if we wanted to isolate that intermediate? How could we do that? So how can we isolate the alkene? And there is a way to do it. So if we want to stop at the alkene, we have to use a poisoned catalyst. Now, the poison is in quotations because that really just means that the catalyst is partially deactivated. Now, there are a couple of catalysts that we can use. We can use something called Lindlar's catalyst. And this is composed of a mixture of molecules, so I'll just draw those out for you. And you don't really have to remember these molecules that are in the catalyst. You can just write Lindlar's catalyst underneath the arrow in your reaction. Let's see. Okay. And then we have palladium mixed with barium sulfate and methanol. So there's quite a few molecules involved in this catalyst. There's also another catalyst that does the same thing, and we call it the P2 catalyst. I'm actually not sure where the P2 comes from, to be honest. But we mix that with hydrogen. And this catalyst is actually made up of Ni2B. So there's 2 nickels bonded to boron. So how does a poisoned catalyst work? Well, if we look at a reaction coordinate diagram, where energy is on the y-axis and reaction progress is on the x-axis, let's look at how this reaction works without the catalyst. So we would have the first step followed by a second step. So we start with the alkyne, then the intermediate is the alkene, and finally at the end we get the alkane. So what the catalyst does is it changes the pathway. So I'll show the catalyst in red here. So the catalyst is going to lower the activation energy of the first step, but not the second step. So it might look something like this, where we've lowered the activation energy between the alkyne and the alkene, so we can easily go from a triple bond to a double bond, and then in the second step, the activation energy is high enough that we can isolate the alkene before it goes on to that step, because there's quite the barrier for that second step. So again, the poisoned catalyst only catalyzes the first step. All right, so let's show what would happen if we performed a reaction where we reduce the triple bond and stop at the alkene. Okay, so we've got our triple bond, and this is the same molecule we saw before. And then we can just write H2, Lindlar's catalyst. Or you could write P2 catalyst, H2. And this would give us the cis alkene, because remember, hydrogen will add across the double bond on the same side. So this is syn addition. But what if we want to get the trans alkene? So what if we want the hydrogens to add opposite to each other? Well, then we're going to perform something called dissolving metal reduction. So in that situation, we use pure sodium metal and ammonia, and we're actually using liquid ammonia, so I'll add a little L in parentheses there. And this is actually going to give us the trans alkene. So the hydrogens add opposite each other. Now, your textbook goes through the mechanism for dissolving metal reduction, but don't worry about it for now. It actually involves a radical intermediate, and we're going to talk about radicals in the next chapter. So don't worry about the mechanism for now. Now, there are some issues with dissolving metal reduction. One is that sodium, you might remember, is very reactive, so it can be dangerous to use. Particularly, it's really reactive with water, so you can't have any moisture present. Additionally, liquid ammonia is very hazardous. It can actually eat away at your skin, And for this reaction, we need pure ammonia. So not diluted ammonia, because otherwise there'd be water, right? And the sodium would react with the water. So unfortunately, this might not be the most efficient or safest way, or sorry, the safest way to make a transalkene. You might want to do that some other way, but it is an option if you're trying to come up with a synthesis pathway. So let's kind of summarize everything we just learned, and we'll draw a reduction map. All right, so initially we saw that we can turn a triple bond into a single bond using excess hydrogen with one of the catalysts we mentioned. Then we also saw that if we use hydrogen and Lindlar's catalyst, we can actually stop at the cis alkene. And then if we wanted to go all the way to the alkane, we could use hydrogen and palladium mixed with carbon. Now we additionally saw that we could get the transalkene using pure sodium and liquid ammonia. And then if we wanted to go to the alkane, we could again use hydrogen with a catalyst. All right. Now, the reason I'm showing you all of these different pathways is, again, in the future, we might use some of these reactions to create a synthesis pathway to get from one reactant to a particular product. And along the way, we might need a cis alkene in order to get the right stereochemistry for our product, or we might need the transalkene to get the right stereochemistry. So these are just good to have memorized so you can later on use them for synthesis problems. Okay, so we'll stop there today. Next time, we will talk about hydrohalogenation of alkynes, and we're going to talk about Markovnikov and anti-Markovnikov addition again. So I will see you then.